This discussion's on inclined planes, and I encourage you to read the front of this sheet because it helps you out a little bit with some of the inclined plane stuff. But things I would like to comment on real quickly is a review of the normal force. Remember, the normal force always acts perpendicular to the surface that it's in contact with. So right now you guys are sitting on your chairs, and the normal force is acting perpendicular to the surface of the chair. So the surface of the chair is horizontal. The normal force is going to be vertically upright. Right? It always acts perpendicular to the surface, and basically it prevents the object from blowing through the surface. Okay, I mean, now obviously if we stuck an elephant on this chair, that would obviously be too much for the normal force to overcome and the chair would collapse. But in normal situations, the normal force is going to counteract typically the force of gravity. Now we're switching gears here and we're talking about inclined planes. And if you think of an inclined plane, basically it's a ramp. Okay, this front page gives you some tips and tricks for looking at inclined planes. The probably most important piece is if we go down way down to the bottom, there's two equations that come in handy. These guys right here. And I apologize, I probably should, instead of saying mg, two little lines, should have said weight or the force of gravity instead of that. But do you guys remember the formula for weight is W equals mg? Ring a bell? Okay. Basically, what ends up happening is on an inclined plane, the force of gravity gets broken into components. There's a component that's parallel to the surface of the inclined plane, and there's a component that is perpendicular to the surface of the inclined plane. And are you guys aware in math that these symbols, the two straight lines represents parallel, and then the upside down T is perpendicular? Are you cool with that? Now you know? Okay. So upside down T is perpendicular. Parallels are the two, like I look at them as railroad tracks. So this is the formula to find out the parallel component of gravity, m, which is the mass, times g, which is 9.8, times the sine of whatever the angle is. And then to figure out the perpendicular component, you take the mass times gravity, which is 9.8, times the cosine of whatever the angle is. Okay, so it's just pretty straightforward. You're breaking into components just like how we broke Ben Studying's backpack into components. Okay. So let's move on down to this real sweet pick right here. All right. Back in the day, we used to look at our x and y axis kind of like this, right? Here was the y, here was the x. Okay. Now we're going to actually tilt the whole x and y axis like so. How are we going to tilt it? Well, basically the x-axis is going to line up with the inclined plane, so this plane here, and the y-axis is going to line up with the normal force. And the reason why we do that is, let me clear this. Oh, that's going to take forever. I should have just done something different. But anyway. Well, you can have that there. It's not a big deal. The reason why we do this is, let me get a different color. If I make this be my y-axis, and if I make this be my x-axis, notice the normal force, the force of friction, and if I had like an applied force, say like to the left or the right, all line up with the x and y axis. Why is that important? I don't need to break it into components anymore. Okay, and I don't know about you, but I'm not a big fan of breaking vectors into components. I'd rather not do that piece of math if I don't have to. And the way to avoid doing it is basically tilt the x and y axis so it lines up with the inclined plane. Now, $1,000,000 question, which force will you still have to break into components if you look at this picture? The weight or gravity, right? Notice it is not in line with the x or y axes. And that's okay, but I got most of my forces in line with the x or y axis. Now, if you don't want to do that and you want to keep it how we traditionally keep x and y axis, you certainly can. It'll work out. You just need to break more forces into components and, in my opinion, do more work. And one thing I found with high school students is you want to do the least amount of work possible, right? And so we're going to try to do that. What I'm going to do is notice here's this weight right here, right? This big old, I'm going to make it a big old arrow, okay? That's the weight. I'll label that with a W, right? There are two components to the weight vector. And let me make this a little smaller. There's this guy right here. And there is this guy right there. Okay? Which of these, the yellow arrow or the blue arrow, would you say is perpendicular to the plane of the inclined plane? Yellow would be correct. No, perpendicular means at an angle of 90 degrees to the surface. So the inclined plane's right here, and the blue arrow's, the yellow arrow is coming straight down like so. So this yellow arrow right there, that is called the force of gravity perpendicular. Okay. The blue arrow, would you say that's parallel or perpendicular to this inclined plane that this box is sitting on? Parallel. So this is called force of gravity parallel. Notice we have formulas on the previous page that tell us how to solve for force of gravity parallel, force of gravity perpendicular. Because what ends up happening is we know, or we will find out, what this angle is right there. That's called theta. And the red arrow here is the hypotenuse of this right triangle that I've created. Okay? So I can just use my trig functions to find out whatever the blue arrow's value is and whatever the yellow arrow's value is. You follow? If you follow, clap your hands. All right, good, wonderful. More than 2, less than 50. Wonderful. Now, just kind of using your brain, you put this box on an inclined plane, and it starts to slide down the inclined plane. Which force would be responsible for causing it to slide down the inclined plane? Gravity, right? And so that's our first question. If the box is at rest, the net force acting on it is equal to, maybe I actually read this question wrong. If the box is at rest, the net force acting on it is equal to, what would it be? If it's at rest and it's not moving, it would be equal to 0. There is no net force acting on it. So the force of friction must be stopping it from sliding down this inclined plane. Okay? Can I erase this picture? Yeah. Okay. I'm going to move on down. Let's look at a question. All right. I'm going to do a little drawing, so hopefully you got your art skills raring to go. It says a 5 kilogram mass is held at rest on a 30-degree incline by some force that they've called F. Okay, they don't really tell us what the force is. They want to know, what is this magnitude of force F? So I'm going to draw a big old hairy triangle. Like so. This is called an inclined plane. And I'm going to put a box on it. We'll put it right here. And it really should be in contact with the surface. It's not floating, but I'm just not a very good drawer. Here's the angle of 30 degrees. Okay. Now, thinking back to free body diagrams, how do I draw in the forces on this box? What's the first first force I draw in? Force of gravity. Which the force of gravity, what direction does it point? Down. So I'm going to draw in the force of gravity straight down. I'm going to label this Fg. That is the total force of gravity in all its glory, pointing straight down. Okay? Then the second question I asked myself about free body diagrams is, what is touching this box? Right? What is touching this box? Well, hopefully you guys are thinking the inclined plane, right? So what forces does the inclined plane provide to this box? Force of friction, very good, but it says it's on a frictionless surface, so I'm going to ignore that for right now, but you're right, it wouldn't provide friction. What else does it provide? The normal force. What direction is the normal force pointed? Normal force. Let's do a review of the normal force. The direction of the normal force is perpendicular to the contact surface.
Yes,
right?
to the right, but like on the...
No, it's to the left. Up.
So, like this?
Yeah.
Is that what you guys are thinking?
No, but I was.
All right, that's the normal force. Notice it is perpendicular to this inclined plane, which is weird because we normally have been doing the normal force, pardon all the puns with normal, normally have been doing the normal force just being straight vertically up because everything's been on a flat surface. But now we're starting to put things on inclined planes. The normal force is always perpendicular to the inclined plane. All right, now I remember I have decided to make my x and y axes in line with this plane, okay? So I'm going to have to break this force of gravity into components. How am I going to do that? Well, I'm going to tell you my what I think is a pretty sweet trick. Right? I'm going to take my normal force line and I'm going to extend it straight down. Okay? This blue dashed line is one component of the force of gravity. Okay? Then once I've drawn that component, I'm going to draw another dashed line that goes left. Thank you. Well, it is. Well, it really shows up differently than on my screen. My screen is more like a booger green. This I would call like a highlighter green. Now, why is this cool? Or why do I think it's cool? This blue line represents what component of the force of gravity? Perpendicular or parallel? Perpendicular. So I'm going to write F sub g perpendicular. What about this sweet green color? Force of gravity parallel. Okay. I want to solve for each of those components. Okay. But before I can solve for that, I need to know, let's see, what's my new color be? Let's do magenta. I need to know what is that angle right there. What is theta? Okay. Why I think this is such a cool trick, what I just did, is because whatever the angle of the inclined plane is, 30 degrees, that is theta, if you follow my way of doing things. Okay? So it's 30 degrees in there. If you get that, clap your hands. Wonderful, wonderful. Okay?
So it's 30 degrees?
Correct. If you do it the way that I do, where you extend the normal force line straight down, even though these lines aren't very straight, straight down, and then you do one going across, that angle in here is going to be 30 degrees, which is the same angle as whatever the incline is. So just for poops and giggles, let's say the angle is 20 degrees. What would be in here? 20 degrees. All right.
Well, that's easy.
That's not too bad then, right? And if you want to know how, I can go into the geometry of it like individually, but to me it's a lot of rigmarole that's not necessary, that we add extra confusion. Okay, but I can explain why if you want me to later. Now the question is, what's F sub g? Right? Because I can't really solve this triangle unless I know F sub g, right? So anyone have an idea how I can figure out that weight? Very good. Weight equals mg. Do I know the mass of this box? Hot diggity, I do. It's 5 kilograms. Do I know what g is? On the g, I do. It's 9.8. So I take 5 times 9.8, and it is 49 newtons. Okay? So F sub g is 49 newtons. I'll just write that right here. Now, if you think about just this using common sense, this box is probably going to want to go like this way, right? It wants to slide down the plane, right? But they're telling us that some mystery force is holding it going this direction, right? I know, that's crazy. Some mystery force is holding this box in equilibrium, so it can't move. Which of these forces, force of gravity parallel, force of gravity perpendicular, would be responsible for causing the box to even want to accelerate to the left? Oh man, that's so big.
I don't have enough colors for this.
So kind of think about it. Who would make it want to move down the plane to the left? The force of gravity parallel or the force of gravity perpendicular? Parallel, right? I mean, I think that makes sense. At least I hope it does. That would be the force that would cause it to want to slide down this plane. It says that it's held at rest, so it's not moving. So I'm thinking, if we can figure out F sub g parallel, we will know what this big honkin' F is. Okay? So how do we solve for that? Well, I'm going to take, very good, the sine of 30 degrees equals opposite, which is F sub g parallel, over the hypotenuse, which is 49 newtons, which we solve for by using this weight equals mg formula. If you do that math problem, I get a force of gravity parallel equals 24.5 newtons. And that would be the answer.